My name is Satoshi Murata. I'm from Tokyo Institute of Technology, and I'm a roboticist. And today I would like to talk about the self-assembling systems. And my talk we have three parts, and the first part is the introduction part, and I will briefly explain the concept of self-assembly and self-reconfiguration. And before I go into the DNA kind of molecular self-assembly stuff, I would like to show you some examples in programmable self-assembly in robotics. And then the second part is molecular self-assembly, which is a result mainly of collaboration with Eric's lab. So you will see some experimental results on mainly error suppression methods, which is essential to use this kind of technology as a fabrication of nanoscale objects. So my point is rather engineering side. And then I would like to conclude my talk about the future of DNA-based nanosystems. Okay, so this is a concept of self-assembly. So here we assume randomly distributed elements, and they should arrange into a programmed order without external help. So, for instance, the proteins can make some molecular machinery, or we can interpret this like this. So these the part with the bird, and this is the flock of bird, and they have some particular behavior. Or self-configuration is a process in which connected arrangement of elements change into another programmed connected arrangement without external help. So this is pretty much like cells which form the shape. For instance, Hydra can regenerate its shape by using this kind of behavior. And the third one is self-repair and self-healing, which is automatic recovery of damage without external help. So this is a distributed case, and this is a self-reconfiguration case. This is much complicated than this type. So here we have to detect the damaged part by some local interaction among the elements. Then it should be cut it off, and then reconstruct the damaged part. So this kind of process is necessary to be realized. And here I'd like to show you a very simple example of self-assembly, which is actually one of the first work of artificial self-assembly. And here this is Hosokawa's work when he was a PhD student, and this is he made a lot of triangular plastic pieces with magnets on it, and he just put it in a transparent box and rotate the box to mix those pieces. And the phenomenon what he expected is to so he wants to observe the process of self-assembly. And so at the initial time, all the triangle is in this form, monomer. And gradually it connects with each other by the magnets, and it becomes dimer, threemer, fourmer, fivemer, and finally hexamer. So there is no more magnets on the surface of this hexamer. So this is regarded as the final product of this process. So as an engineering, we want make this hexamer final product as much as we want. And this is the result of experiment. Actually, this is a simulation result of simulation based on law of mass action. And here you see at the initial time, only the X1 monomer exists, and it rapidly decreased, and it becomes instead it becomes a dimer and threemer. But those, for instance, two dimers and threemers can make a fivemer. But when the fivemer appears, most of the monomer is consumed to become other species. So when the fivemer appears, there are no monomer to fill this gap. So at the final stage, we have some hexamer, but we have other species of the byproduct of the this process. So recently, Eric Kravis at the Washington University, Seattle, renovated his Hosokawa's model. So he changed. He doesn't change the basic design, but he puts three motors which can enable or disable the magnets on the edge. And it also has a microprocessor on it, and that microprocessor can communicate with the connected one by kind of infrared optical device. And this is the thing. And he put this module on an air hockey table and steered them by many fans around the table. And this is an actual photograph taken by a camera on the ceiling. So here you see the hexamer formation self-assembly. But but here we actually have more freedom to design this process to achieve better yield. So, for instance, if you allow only dimers and inhibit to become threemer, then all the species becomes dimer first. Then those can be connected to make a hexamer. This kind of grammar improves the yield pretty much. And also, you can design various kinds of self-assembly on the processor. So that one is a kind of distributed, separated module can gather to make something. But this is my machine called Fracta. This is not that type machine. This is a self-reconfigurable robot. So in this case, they must be connected at least. But they can change their local connectivity by using the magnets and the electromagnets controlled by the onboard microprocessor. So here is the mechanism of self-reconfiguration. So these are the electromagnets of, permanent magnets of one module, and this is the electromagnet of the other module. So they are connecting here by the electromagnet. But if the polarity of electromagnet is reversed, then this connection is disabled. And at the same time, this electromagnet is activated, then it is pulled like this. So repeating this kind of switching, you can change the location of the bonding. And of course, you can break the connection or transporting a module on the edge. So actually, this is this kind of unit is able to make a self-reconfigurable mechanical system. And so here we have 11 units, and those cables are just for power supply, and they are now talking with each other by flashing light, and they are now becoming a triangle, which is a target shape for this system. And here we have a sphere unit just hidden behind the cables. And to mimic the faulty situation, I just cut off the power for this unit. Then it is detected by the connection and ejected automatically. Then the wall system is activated now to recover the shape again. So here the spare one comes and the shape is recovered. So this is the first example of artificial self-repairing system. And here another example of self-repair. So here I cutted the other guy, and he's ejected, and now they are activated to recover the shape. But the process is quite different in this case. Many guys have to move to find out their new places in the triangle. So it's a kind of stochastic algorithm to use. And here the kind of similar algorithm is extended to make more complicated shape. But we assume the same constraints on our design of program. It must be homogeneous. So all the units must be driven by the identical program. So, and it must be parallelly executed. And we allow only the local communication. So, so they can talk to its neighbors, but not just neighbors. So they cannot know what is the global shape or where it's damaged. So those kind of information must be transferred by local inter-unit communication. All right, so that's the thing I want to make by molecule. But there is a huge gap, and I'd like to talk about some DNA implementation. And as Milan told you that DNA provides a kind of ideal material for nanoscale machinery. So that there are a bunch of advantages of the molecule. First, it's predictable. It's good to design. And also, it's chemically stable and safe in a short length. So it's good for good to use as a structure member of the machinery. And also the important point is the specific connection between complementary bases, as you know, and we have useful toolbox developed in biotechnology enzymes. And here is some example of self-assembling DNA motifs. And I'd like to explain some experimental results which is done as a collaboration with my lab and Eric's lab. And here we implemented a one-dimensional cellular automata. And so this is a one-dimensional array, and each box has a 0 or 1. And cellular automata is a kind of calculation in which the time development is determined only by the local interaction among the cells. So if the first line denotes the initial state for this calculation, then the second line is determined by applying this local rule. And if you look at this rule carefully, the result doesn't depend on the color in the middle cell. So for instance, this one has a black here, but this one has a white here. And both of them have the same result. And this one and this one is black, regardless to the color of the center. So to implement this, we just need two sides, and this is implemented by Paul and Eric as a DNA type cellular automata. And so this is we already seen. And here's a picture of the similar one, but maybe you notice that this is a large, much larger than the previous one. This one is designed by Kenji Fujibayashi and Eric, who spent a year in Eric's lab, and he slightly changed the design of molecule. And so in the previous case, the tiles are placed horizontally, but he just changed it vertically. Then the quite large Sierpinski crystal appears. There are some reasons behind this, but we haven't verified it yet. And so, as an engineering point of view, it's quite important to know and control the error rate on this kind of nanofabrication. So, if you want to make something reliable, then we have to suppress the error rate quite low. And so to do that, the evaluation of the quantity of the error on the lattice is quite important. And we have some experiments to do the measurement. So here we have a scaffolded DNA origami and some programmable adapter which represents the initial starting bit pattern, and we apply the Sierpinski rule set and some boundary ribbon tiles. So here, this is a kind of the most complicated nano system. Here we have 7,000 base pair for the scaffold DNA origami and 200 kinds of staple strands woven in the origami, and seven kind of tiles. So all of those DNA materials are mixed in tube and annealed. Then we'll have this kind of structure. And if the self-assembly goes perfectly, then we'll have this kind of ribbon structure. So if you have a full, this is a periodic pattern we expect, and if we have a full cycle on the ribbon, then we have error rate 0.25%. And so if we can compare this template with the experimental results to evaluate the error rate. And this is the experiment result. And so you see a good correspondence with the experimental result and simulation template. And by comparing those images, we can actually count the error rate. And here's the result. And this is compared with simulation, which is the same simulator which Eric already showed. So in that simulator, the thermodynamical constraints are considered. And in this ribbon simulator, annealing temperature profile and concentration change of each species, type, are carefully reproduced. So we expect that the crystal growth in the simulator is quite similar to the real one. And so we can also count the error numbers of error on the simulation, and we compare the results. And this is the simulation results, and this is the experiment results. So in the before the 15th row, the error rate is almost the same. So that the simulator tells us what happens in the micro tube quite well. And if you see this part, the error bar is quite large, and the error rate itself increases rapidly. But in the simulation, we do not have such phenomena. The large error bar is because of the around here the crystal growth is actually stopped because of the lack of the monomer DNA type. And and also in the real tube experiment, we have some spurious nucleation of the tiles, which is not initiated by the origami structure. So that kind of error absorbs the tile, and which destroy the constant balance between the DNA tiles. That makes the worse error rate. And so let me explain some detail of the errors on the DNA tiles. So here is one of the most typical error, which is a mismatch error. So from the initial structure, those tiles are perfectly assembled. But here, the new tile comes, but it has only one correct bond. So the stickiness of this tile is quite weak. So it must be fall off. It must fall off fast. But before it is falling off, another tile comes and connect here with two bonds, then both of those two pieces are stabilized now, so there are no chance to get out of this mismatch. So after this mismatch occurs, the result of the computation is not correct. And the second type of error is called facet error. So in this case, two DNA tiles are attached side by side by chance. Then it can grow another layer of facet. But the result of this growth is no relevance with the previous growth. So it also contains some mistake in the calculation. And the third one is a nucleation error. Here, we want the growth only from the initial structure, but this is a spontaneously started growth. So this should be avoided. And the first method to reduce those errors is proposed by Eric, and it is called proofreading tile set. And here, so each Sierpinski tile are divided into four small pieces. And actually, so it requires 4 times larger lattice. And each of the newly introduced sticky ends are unique, so different from the original one. So in this, so by this implementation, you can reduce the rate of error because when one tile has come here and it is mismatched, then the next tile does not stick to the place without making additional error. So by using this kind of proofreading, we can improve the error rate like this. So without proofreading, the growth speed is proportional to a square of error rate. So, but by using the proofreading, growth speed is proportional to error rate. So if the error rate is 1%, it means that by using a proofreading, you can speed up the growth 100 times. That is quite a big difference. And here is another mechanism of error suppression, which doesn't require a change of size of the tile. And here we introduce another layer of tile, which actually controls connectivity of the input and output strand. So the idea is if both of the input side of the DNA tiles are correctly matched to the structure, this is that shows that situation, then those strands are connected to the lattice, and at the same time, those partially covered part of the covering tile is removed by the connection, and only when two of them, both of the input strands are removed, then the cover cannot remain on the tile. Then it is dissociated from the tile. So the dissociation actually opens the next output strands, which allows the next association of the tile to the adjacent lattice point. And when the this tile is has a mismatch, then one side of the covered tile can be removed, but it's not enough to remove all the tiles. So it remains in place, and this this doesn't allow additional association of the other tiles. And the bonding strength itself is quite weak, so this complex will be dissociated. So by this mechanism, we can reduce the error rate further. And this shows the result. So this is without proofreading. And this is, I haven't explained but in my talk, but this is a kind of partial proofreading. And if you apply the layered tile mechanism, then we don't have any errors, do not sacrifice, and without sacrificing the growth speed. So maybe this is the time to conclude my talk. So I would like to explain some future of the DNA-based nanosystems. So the next target is to realize a reliable self-assembly, which we are now working on. So, and also we want to, so as Milan's robot, we need some activation mechanism or internal states on each tile that will improve the yield and the programmability of the system pretty much. So one of the next targets is the activation mechanism and internal states on the DNA components. And also, control the environment for self-assembly is important, I think. So the prior work all done in a tube, but we can use some kind of microfluidic device like this to precisely control the environment of self-assembly. And also we can do some complicated process of self-assembly, of hierarchical self-assembly by using this kind of device. And the other kind of target is the 3D lattices. And to do this, we need a precision 3D component, and I think it's not very difficult. And also, integration of functional elements. Milan already achieved some wonderful example of the integration, but we want to pursue or achieve it in larger scale. So this is just my speculation. So this is the final slide. In a few years, three-dimensional DNA crystal will be here, and reliable DNA-based devices are also will be available. And in 5 years, in a sense, it is already done, but the simple DNA-based integrated systems will be realized. And in 10 years, DNA-based nanorobots for some practical application, such as smart drugs, DNA-based optical electric application will see those kind of things in 10 years. Okay, that's all I have to say today.